Today I'm going to talk about LeetCode question, alien dictionary. So there is a new alien language which uses the Latin alphabet. However, the order among letters are unknown to you. You receive a list of non-empty words from the dictionary, where words are sorted lexicographically by the rules of this new language. Derive the order of letters of this language. Okay, so I think that's kind of best explained using this example here. So we have these list of words, and this is the ordering of the words in this alien language. In the alien language is lexicographical order. So explanation is from this first word, change colors here, from this first word and second word. If we compare them, and W is the same, R's are the same, T, the word with the T in it comes before the word with the F in it. So in this alien alphabet, T comes before F. Okay, so T come followed by F. When we compare the second and third word, so you see the word that starts with W comes before a word that starts with E. So we can see W leads to E. For these two words, we can see E is saying whatever, R comes for T, so R, T, okay. And this last word here, you get E becomes for R, okay. So we return WERTF, which kind of would be like A, B, C, D, E in our language, but in this alien language, W comes before E and E becomes for R, etc. So notice how I drew these arrows here, okay? So if I compile them together, we saw T comes before F, okay? And then W before E, and then R before T, and we already have T here, so we just pop R right in front here, and E comes before R, so we can link that to here, and that's how we get the order WERTF. So we can kind of see this is actually a graph problem here. Okay, so that's how we're going to approach this. So we're going to compare two words at a time. So like these two and then these two, okay, letter by letter, and see which letter comes before in this alien dictionary. Okay, and why two at a time? Well, if we think about it in our own English language, A, B, C, we see A comes before B, so that's 2, and then next to B comes before C. Okay, and we only need to compare 2 at a time, because if A comes before B and B comes before C, therefore A must come before C. So that's why we're only comparing 2 at a time. Okay, so that's kind of the crux of that here. So first step we're going to do is build an adjacency list where there's a letter. The format of this adjacency list is going to be a dictionary where there's going to be a letter, and everything after the letter and everything in the adjacency list here will be whatever comes after this letter. So for example here, if we have R, what's going to be in here is T and F. Okay, so we're going to build our adjacency list first, and then using this adjacency list we're going to do topological sort. And topological sort in a graph, what it does is it helps us order the graph based on what should come first in the graph, based on there's no incoming edges here, and what should come last in the graph. Okay, so for example, if we have like this node, this graph here, topological sort would say in order to get to these two, we need to get to this guy first. So this would be number 1, and these two, since their priority is kind of the same, it would be and 3. So that's what topological sort will help us with. Okay, and yeah, so let's look at these criteria here. So you may assume all the letters are in lowercase. Okay. If the dictionary is invalid, if string A is prefix of string B and B appears before A. So what does this mean? So if we have string B here and it's like apple and string A, app. So string A is a prefix of B because both contain app and then app. So A is a prefix of B. And since B comes for A in our alien dictionary, this is invalid. Okay, it doesn't make sense. Like, just think about this alphabetically in our own dictionary, which would come first, app or apple? Obviously, app. So that's what that second one means. If the order is invalid, return an empty string. So, what constitutes an invalid order? Well, if we have a cycle, basically. So like if A should come before E, but then also in a dictionary, E comes before A, that doesn't make any sense. Therefore, this dictionary is invalid. There may be multiple valid order of letters. Return the smallest in normal lexicographical order. Okay, so this is kind of a tricky one here. So how do we, so for example, if we have the dictionary A, Q, what's this, Q, A, and then T, R. Okay, what would the order of this dictionary be? Well, we can either have Q, A, T, R, or Q, A, R, T. Okay, because the ordering of these two is kind of ambiguous, so if they're ambiguous, then we can kind of put them in any order in the alien dictionary here. But this fourth condition, if this fourth condition is saying if there's multiple valid orders, return the smallest in normal lexicographical order. Normal meaning our alphabet. So what we would actually choose is this guy here because R comes before T. So how are we going to determine the normal lexicographical order here? So with topological sort, what we're going to use is min heap. And with this min heap, we're able to extract the smallest letter according to our alphabet every time. Okay. This will make more sense in the code. So if the letters in one string are of the same rank by default and are sorted in human dictionary order. The letters in one string are of the same rank by default and are sorted in human dictionary order. Okay, so I assume this says if we have this one string in our input here, like Q, E, and then nothing else here. Then it wouldn't be QE, I guess it would be EQ. I guess it would kind of take care of that there. But anyway, yeah, that's the conditions we have to follow. So this fourth one is especially important. Okay, so how are we going to approach this problem? So I kind of outlined the steps here. Create an adjacency list. Seems easy enough. So with our adjacency list, I'll go into one more detail. What we're going to do is compare two at a time. Okay, so for example, we have WRT, WRF, okay, and then we compare them letter by letter, okay, and find the first difference between the two. And that first difference implies this previous string, this previous character will come before this next character here. Okay, so if we compare the W's, this doesn't tell us which letter comes first in an alien dictionary, so we scratch that. Same with R, scratch that. And then we see T and F, they're different, so obviously T will come before F. And that's basically what we're going to do to create our adjacency list here. And for 2, our topological sort, what we're going to do is, along with our adjacency list, we're going to keep common edges. Common edges dictionary, where it's going to be like letter and number of uncommon edges. So what's should be curly brace. So what's the point of this? Well, we're going to keep track of incoming edges. And if an incoming edge for a node is 0, then that means we should, or letter, I mean instead of node, then that means we should look at that letter first. Okay, it makes sense. Like look at this example. I'll switch to black. So let's look at this example here. So what would this incoming edge look like? So this would look like W1 or 0. There's no incoming edges. Okay, this is only outgoing. E would be, W would be 0, E would be 1, R would be 1, T would be 1, and F would be 1. Okay, so in our topological sort, we're going to pop from the min heap. Okay, and in our min heap, we're only going to store characters with incoming edges of value 0. So we're going to pop this, and we're going to add this to our result here. Okay, and then before we move on to the next iteration of our topological sort, we're going to do all of W's children and then decrement their number of incoming edges. So W's children would just be E in this case, so this would be decremented to 0. Okay, that's because we already popped W, added it to result, now it's no longer in consideration. So now we're going to look at E. So in our min heap, what are we going to pop now? Well, we're going to pop E because it's the only element in min heap so far, with the number of incoming edges is 0. And every time we decrement, and if the number of incoming edges becomes 0, then we add that to our min heap. So it will be E next, then we look at E's children. It's R, so we decrement that, add it to our min heap. Okay, now next iteration of topological sort, we pop, which would just be R. Look at R's children, decrement, and so on. Okay, so that's how we're basically going to do that. So what's the time complexity of this? Well, obviously popping from the min heap would take kind of a log n time, where n is the total number of characters. But the real bottleneck is doing the comparison between each word 2 at a time. Okay, and so that would be O of m times n, where m is the number of words and n is the number of characters. Okay, and that's pretty much it. So now to code this up, so what I'm going to do is first off import heap queue, so I can create my actual min heap. Okay, now let's get onto the real code. So I'm going to create an adjacency list here as a dictionary, and my incoming edges count dictionary. Okay, and what I want to store in these two is each character that in words. So we're going to scan through words, scan through each individual word in words, and add them to our dictionaries here. So word in words for character in word, if a character is not already in the adjacency list, then initialize it. Adjacency char is going to be equal to, let's have it as set instead of an array, just because it's easier with a set to not add duplicate characters. And if a character not in incoming, then do the same thing. So incoming adjacent, or sorry, char is going to be equal to 0. Okay, great. So we have that, and now what we want to do is compare 2 at a time. Okay, so for I in range, the length of words -1. Okay, we're going to stop short because we want to compare 2 at a time here. So word 1 is going to be like that, colon there. So word 1 is going to be equal to words at I, and word 2 is going to be equal to words I plus 1. Okay. And now what I want to do is get the smallest length between the words, between the 2 words, equals min length of W1, length of W2. Okay, and now I want to check, using the smallest length, check if W2 prefix of W1 and W2 is smaller than W1. Okay, so if length, I check if yep. So if length of W1 is greater than length of W2, so I'm doing this in, remember this case of apple, and then app. Obviously, app should become comfortable or apple, so we're just checking for this. And if this case turns out to be true, if W2 is a prefix of W1 and W1 is bigger than W2, then obviously return empty string because it's invalid. And W1 and so if W1 is greater than W2 and the prefixes are the same, then return empty string. Okay, cool. Now let's start actually compare letter by letter. So for J in range, smallest length, if W1 at J is not equal to W2 at J, then what we want to do now is add that to our adjacency list here. So adjacency adjacency at everyone add backup. Okay. And then obviously after that we want to break. Okay, we don't want to keep comparing. Okay, cool. And now, so we filled up adjacency, what about incoming? So let's go through adjacency here. So, and if a set is empty for any letter in adjacent, or actually, yeah, so this counts incoming. So what we want to do actually is while we do this, we actually want to fill up adjacency too. If this letter not already in our adjacency for this letter, what you want to do is incoming for its next letter here is going to be equal to self plus 1. Okay? So basically what we're doing is if it turns out two characters are different, I want to map like A, B or something, then A will have an adjacency list and it'll contain B, and if B is not already in adjacency list for A, then we increment B's incoming edges by 1 because A will be pointing to B, okay, and then number of incoming edges for B now is incremented by 1 because of this A. Okay, and we add this condition because we don't want to double count. If we already have this mapping between A and B, we don't want to increment it again in case we see it again. Okay, so yeah, that's pretty much it. Now let's do our topological sort here. So first I'm going to have my heap. Okay. Oops, sorry. And then heap heap, I'll just heapify that. Cool. And then what we want to add stuff to heap. And what we're going to add any letter with incoming edge of 0, because obviously that's going to be the first letter we gotta look at. So I'll iterate through my incoming dictionary. So eval in incoming dot items if val is equal to 0, then heap q dot heap push heap, and I'm gonna push the letter which I denoted as key. Okay, that's pretty much it here. Now let's do some result variable is going to be empty string so far, and then we're also going to keep a visited set so we don't visit the same letter twice. Okay, like if R maps to A and B and Q maps to A and C, we don't want to visit A twice. So yeah, so while length sub heap is not 0, I'm gonna pop, so char character is gonna be equal to heap q dot heap pop heap. Okay, if char in visited, then we're gonna skip it. Continue. Okay, or else what we're going to do is update a result with char, okay, and then add this character to a visited. We officially visited it now. Okay, and now what we want to do is get our list of children for char from our adjacency list and iterate through them. And since we just put this char in our result, that's one less common edge for each of its children. So for child and children, what we're going to do is incoming child equal to incoming child -1, and if incoming child is now 0, we're going to add it to our heap. Push on child. Okay. Yeah, and that's pretty much it. And whenever we pop it from the heap, it's basically gonna be in the lexicographical order of our normal English language. So that satisfies condition 4 here. Cool, so that's basically the topological sort. And finally, let's return everything. If the length of the result does not match that of the length of, say, incoming, because remember it contains all the characters and we want all the characters to be in result, then obviously there must have been some kind of loop detected in our topological sort here. So we're going to return that. And then finally return result. Okay, so yeah, that's pretty much it there. So I'll try running my dry run. Okay, looks good. I'll submit. Okay, cool. Thanks for watching.